That'd be pretty cool. I didn't say it would be useful. All right, everybody, here we go. We're going to talk about recursion. So I'd love to see your eyes up here, everybody, because there's nothing on your screen that it covers recursion unless you're looking it up ahead of me. Thanks. Recursion is when a method calls itself. And this might sound like a bad idea, like maybe you'd get in an infinite loop and crash or something. But there are many problems where recursion makes a problem simpler to do than if you don't have recursion. That said, anything you can do with recursion, you could also do with regular loops and vice versa. So it's not like it's only possible to do things this way, but recursion, recursive method has two properties: one or more calls to itself, and a way out, which we call the base case. Because if you don't have a way out, then you've set up a loop that goes forever. Imagine if you had a method that called itself, it would just call itself and it would never stop. So that would be bad. And you'll accidentally do it, and it's okay. REPL just croaks, claims it runs out of memory or something. But so this will be on the test. What two things does every recursive method have? A call to itself and a base case. Here's an example. So we just did factorial using a for loop. Here's factorial using a recursive method. So we're calling factorial with a number. And if the number is equal to 0, we return 1. That's the base case. But if we're not returning 1, we return the number times the next one down. See, this is calling itself with a different number. So if we called factorial 10, it wouldn't do the if statement because it's not 0. It would do return 10 times factorial 9, and it comes up with a 9, and the 9 is going to return 9 times factorial 8, and so on all the way down till there's a 0. And just so you know, mathematically, factorial of 0 is defined as 1. So that's just how they defined what a factorial is, and therefore it would finally return 10 times 9 times 8 all the way down to 1. Yeah. Yes, it is exactly what you just did if you did the warm-up. It's just maybe a little cleaner code, a little tighter. So this is the call to itself, and that's the base case, right? We got a call to itself, and the important part there is not the n times. I mean, that's what you had to do if we were doing factorial. The important part is that there is a call that calls itself somewhere in it. That's what makes it recursive. So I'm running this. I'll show you what happens with when we call factorial 4. So first, factorial 4. 4 is not equal to 0, so it calls 4 times factorial 3. And factorial 3. 3 is not 0, so it calls 3 times factorial 2, and so on. Gets down to 1, and then finally it sends factorial 0 over, and that returns a 1. And then up the chain it goes. And so it's 1 times 1, 2 times 1, 2 times, 3 times 2, and then finally 4 times 6. Anyway, that's less easy to follow, but you get the idea. Here's another example. Let's try to figure out what this would do if we called it. This is printing things instead of multiplying things. But right now it looks like it prints a number and then a space. And then if the number is greater than 0, it calls it again with down by 2. So we call recurse with 5. It's going to print a 5. Checks the base case. 5 is greater than 0, so it calls it with 3. So then we print a 3. Then we call it with a 1. Then we print the 1, and 1 is greater than 0, so we call it with a negative 1. It prints the negative 1. And then finally, n is not greater than 0, so it doesn't call itself anymore, and it's over. I made these lines small because it wouldn't fit otherwise. Questions? These things are often like, super obvious after you've done them, and then when you're given a problem, like, do this with a recursive method, and you're just like, it's okay. remember you've got the base case and a call to itself. That's how we do recursion. Here's a Fibonacci series done with a recursion. So I don't know if you remember the Fibonacci sequence goes 1, 1, and then from then on it's just add the previous two numbers. So we get the 2 by adding 1 plus 1. We get the 3 by adding 2 plus 1. We get the 5 by adding 3 plus 2, and so on. So this method gives you the nth Fibonacci number. I could say I want the 10th one by calling itself all the way back till it gets to the 1. So the base case is kind of a double base case, and you're allowed to have multiple base cases. Base cases. If n equals 1 or n equals 2, then return 1, because that's these first two Fibonacci numbers, and then otherwise return the previous two numbers added together. So Fibonacci n minus 1 plus Fibonacci n minus 2. Sometimes things seem backwards. This one is okay, right? Countdown. You send a number, it prints the number, and then it calls itself to print the next lower number and so on. So this one prints 5, 4, 3, 2, 1, 0, no problem. Check this out. This one is slightly different. The print is after the recursive call. So this one is actually going to count up from 0 to whatever number you call. This is because the print call is after the recursive call. Take a look at the difference. This one, we're printing the number and then checking if we should be recursive. This one, we're checking if we should be recursive, and then we're printing. When that happens, the printing all kind of stays on the side until it's over, until all the recursion is over, and then it kind of unspools out in reverse order. We're going to trace this one. So we call countdown 5. 5 is greater than 0, so it calls countdown 4. Nothing's printed yet. We call it with 4. 4 is greater than 0. We call it with 3. 3 is greater than 0. We call it with 2. 2 is greater than 0. Call it 1. 1 is greater than 0. Call it again. Now, finally, 0 is not greater than 0, so there's no more recursion. And then it prints all the results out in reverse order. It goes right back up the chain. So it keeps going until it stops, and then it goes backwards. Yep, it keeps going until it stops, doesn't print a thing, and then it kind of unwinds itself backwards. Is that the same with all recursive methods? No, it's when the print is after the recursive call. See, what I was saying was, if the print is before the recursive call, it goes in the order you would expect, just forwards. But if the print call is after, it goes backwards. So it's a little bit hard to generalize, but in general, if the recursive call is before some other thing, then they're going to go backwards. Yeah. So anyway, this prints out in reverse order. Folks, I'd say it's a good idea to trace these on paper rather than to try to do them all in your head. Lots of times there's modulos, and there's you're doing odd numbers, even numbers, you're skipping numbers. It just makes a lot more sense to try to write it out than to try to do it all in your head. And then, as I just said to Quincy, in terms of the forwards or backwards thing, the key question is whether the print call is before or after the recursive call. But there is not some single blanket rule that applies in every situation. All right, so for the rest of today, we've got a coding bat 6 problems. I know we're going to do 6 recursion problems in coding bat, and then I've got 4 REPL assignments I'm going to ask you to do. So I'd like you to go on to coding bat right now, and we're going to do the first 6 recursion 1 problems. Please remember to log in before you start doing them. Otherwise, you won't get credit. I'm not going to log in because if I did, then all the answers would be there. So I'm going to also stop